Hello Mechatronics students, this is Andrew Dahlen, and in this video we're going to be talking about the dreaded series parallel circuits. Dum dum dum. Alright, so some people have a real problem with series and parallel circuits when they get combined and intermingled with one another. And this does happen in the real world, that we have devices that are connected both in series or in parallel, and it's a big mix. So when working through these, there's some different tactics that we're going to use, and I'll go through and demonstrate them. So for this video, we're going to follow along. This is worksheet number 1, dealing with series and parallel circuits, and I'm basically going to walk you through the solution on how to analyze a series and parallel circuit. So let's get into it. Okay. So when working with series parallel circuits, this is a combination. We have some elements that are in series, like this is in series with this one, right? It's a straight line. The electrons have to go through this resistor in order to get to the next resistor, right? That's a series combination. And then we have elements that are in parallel, where we have a parallel branches of this circuit. So what I encourage people to do, especially when you're just getting used to it, is to go through a process of redrawing the circuits. And the key thing that we need to know is when we look at the formula sheets that we've provided, there is no like series / parallel circuit analysis formulas. You can only use either the series for those elements that are connected in series, or the parallel formulas for those elements that are only connected in parallel. So that's the trick that is going on here. So to help out with this, I don't even worry about the table of it at this point. We're going to go through and show you guys how to redraw the circuits so that we can begin solving for things that are directly in series or parallel. So I'm just going to redraw the circuit on another sheet here. Just give me a second to knock this out. Okay, so now I'm going to populate the information. Resistor 1 is 2 ohms. Resistor 2 is at 3 ohms. Resistor 3 is at 12 ohms. Resistor 4 is at 6 ohms. And finally, resistor number 5 is at 1.5 ohms. Okay, so the reason for redrawing this is that we need to find out what is in what I would call simple series or simple parallel. So we're going to take a look at these and say, okay, what is just straight up simple series or simple parallel? And when I look at this, I could say, okay, well, is resistor 1 and resistor 3, they kind of look like they're in parallel, but it's not simple parallel because you've got another element over here, right? So what I'm getting at is we can say, you know what, resistors 4 and 5, they're absolutely in series, right? They're connected through. That really looks a lot like this sort of series circuit where the electrons have to go through one to get to the next one and through the next resistor to go on. So I would say that resistors 4 and 5 meet the definition of what you call simple series. So I'm going to circle those and say, you know what, these guys are in series. And therefore, the resistance totals are additive. Resistance is equal to 1 plus the next. All right, so we can say that resistors 4 and 5, their total is going to be equal to resistor 4 plus resistor 5. Excellent. And we can do that math here pretty simply. 6 plus 1.5, we can say that a resistor 4 and 5 is going to be equal to 7.5 ohms. Excellent. At this point, we can simplify the circuit. And we're going to redraw this and move forward and show this guy as resistor 4 or 5 as a little bit simpler. So again, we have our 24 volts, 0 volts, and our ultimate goal here is get down to just one value of resistance. Alright, now this is where the key stuff came into play. We were able to simplify one of these resistance values. Put my little nodes in there. And this becomes the equivalent of resistor 4 and 5. And it has a value of 7.5 ohms. Okay? So, in a similar deal, let me just draw that line. So that's 7.5 ohms went right there. It was these two. We recognized that, oh, those guys are actually in series with one another, so we can add them together, and we get 7.5 ohms. Now, the next thing we can look at is, are there any other resistors that are in simple series or simple parallel? And we probably could have done this in one step, but at the beginning I'm just pointing out this way. Like these two guys, right? Resistors 2 and 3, they are also in series, so we can treat them as such. So I'm going to make a little line that's going to bring me back here. Okay, and I'm going to say that resistors, those are series. So resistors 2 and 3 are additive as well. So we can just simply do the math on those, add the two together. 3 and 12, that's 15 ohms. Excellent. So we can then redraw that circuit again. And what we're doing is breaking it down and simplifying the circuit. Alright, get those nodes drawn in. And this is resistor 1 at 2 ohms. This is resistor 2, 3. And that is at 15 ohms. And this last one was resistors 4 and 5. And that was at 7.5 ohms. Excellent. Okay, so we've gone from having 5 values of resistance, and we're slowly working on it. Oh, I was off camera there for a little bit. We've got it boiled down to 3 resistances, and, well, looking at this, we can look at the formula sheet and say, oh, okay, well, now those 3 values appear to all be in simple parallel. There's nothing else going on. So we can then diagnose and say, yep, all these values are in parallel. So at this point we would have to use that strange equation for resistance totals in parallel, and it's this guy here. So we can break it down, and what we're going to end up with is 24 volts and 0 volts and one value of resistance that's marked as resistance total. But to get there we have to apply that formula that resistance total is equal to the 1 over, I'm just going to sub the values in here, so 1 over 2 plus 1 over 15 plus 1 over 7.5. Okay, so we'll go back to our calculator here and pop in a bunch of values. Let's see, I'm going to delete all the history on there. Neat thing with the Windows calculator, when you maximize it, it gives you this history of all the things that you did. So 2 was one of the values. I'm just going to hit the reciprocal on that. That's great. Clear it. That pops over in the memory there. 15 was another value. What's the reciprocal of that? That's great. Pops over and saves it for me. And clear everything out. 7.5. Oops. And what's the reciprocal on that? Okay. So I've got those numbers all figured out what their reciprocals are, and I'm just going to run back to the paper copy here to show. This ended up being 0.5. The 1 divided by 15, the reciprocal of that was 0.066. And the reciprocal of 7.5, or 1 divided by 7.5, was 0.133. Okay, so I need to add all of those up and then figure out what that reciprocal value is. So back to our calculator here, and I can punch them in 0.5 plus 0.0666 plus 0.133. All right. Something weird happened here. Okay, so that looks correct. And then I want the reciprocal of that. So just before I get anything written down here, these all totaled up to 1 divided by 0.6996. That's my resistance total. And I can figure out what that reciprocal value is by hitting 0.6966 and hitting the reciprocal button. Back to the calculator here, hit that reciprocal button, and the total resistance in this case is going to be equal to 1.429. Excellent. So that was a lot of mucking around just to figure out that my resistance total is 1.429 ohms. And that redrawing of the equation certainly helps us figure out what our total resistance is. You know, we can, again, only using series or parallel formulas to break it down and get it boiled down to a simple resistance total value. So now we're going to take and work this backwards. So if we're looking at our sheet back here, the original equation, the original circuit, we can put that in here. We know that our resistance total is 1.429. And we know all these other values: 2 ohms, 3 ohms, 12 ohms, 6 ohms, and 1.5 ohms. All right, so when it comes to these series parallel circuits, you cannot simply plug in the numbers in one fell swoop equation. We have to think about what is in series and what is in parallel all by itself and break it down that way. The other thing we can do in here is to put our other known values in here, which would be total voltage. This is 24 volts. Okay, so now we're going to break this down a little bit further and look at, well, how can we now use that information and solve for all of the voltage values and current values in this sheet? So let's take a look at that. The easiest way, once we've broken it down to its simplest elements back here, the easiest way to find, voltage and current throughout the rest of this is to work backwards. Start here, figure out what the voltage currents are at this point, then move to the previous drawing, figure out the voltages and currents are here, then go back here, figure out voltages and currents, go back here to the original, figure out voltages and currents. So that's what we're tracing down. We know all the resistances, we just need to find voltages and currents, and it's an exercise in Ohm's law. So let's go through this and figure out what our voltages and currents are in the rest of the circuit. Okay, so here we have 24 volts, 1.429 ohms. We can use Ohm's law to figure out what is the current in this circuit. And current is voltage divided by resistance, so 24 divided by the 1.429. And in this case, the current that's flowing in this circuit, the IT, is equal to 16.794, and that's going to be amps. So I could probably round that up to like 16.8 amps. All right, that's the total current traveling through the circuit, 16.9 amps, or 16.8 amps. Okay, let's push that information forward back here. And actually, this is pretty straightforward too. We can go through and find out, we know that this is a simple parallel circuit. We know resistance in each branch, and we know that all these amps should add up to 16.8 amps. Okay, so let's go through this and figure them out. 24 divided by 2, we're going to have 12 amps in this first branch. It's traveling this way. Again, we're just using Ohm's law. 24 volts divided by 2 ohms. There we go. 24 volts divided by 15. Can't do that one in my head. 24 divided by 15, that's 1.6 amps. It's traveling in this branch. Then finally, 24 divided by 7.5 ohms. And that's 3.2 amps. So we can see all of these should then add up to about 16.8. And it looks pretty close. Let me just actually go through it in the calculator. 12 plus 1.6 plus 3.2, 16.8. So all these amperages add up to our total current, which is excellent. All right. Now we're just going to take all those amp values and push them up to the other circuit. So we'll go up here. This was 12 amps in this branch. This was 1.6 amps in that branch, and 3.2 amps in that last branch. Okay, so at this point we can start to look at the individual currents that we have going on here. Individual currents and voltage drops, I guess that's what we're getting at. Okay, so we would know, because in a series circuit, these two resistances are in series, that they're going to have the same exact amperage. Likewise over here, these two are in series, they're going to have that same 3.2 amps running through it. So we can actually move all this information forward. 3.2 amps, 1.6 amps, and 12 amps. And from there, we can figure out what their voltages are going to be. This one's pretty straightforward. There's one resistor, it's in parallel, so the voltage across this resistor is going to be 24 volts. Makes sense? It's connected directly to your 24 volt source. So that one's fixed. These guys are going to be a little bit different. Again, in series circuit, your voltages are additive. Okay? So we know that these will total up. In this branch, they should total up to 24, but we're going to have some voltage across here and some voltage across here. We do know that they're at the same amp values. So we can use Ohm's law to figure out what is the current in here, and the voltage. And voltage is equal to I, current, 1.6, times R, 12. So again, punch that into the calculator. 1.6 amps multiplied by 12 ohms, I get 19.2 volts across resistor 3. Now resistor 2 should have the rest of it. So if I do that, 3 ohms times 1.6 amps, 4.8. And there we go. That's that point we're trying to prove is in a series circuit, and that's what this is. Resistor 2, resistor 3 are in series. Their voltages should total up to the total voltage. So there we go. 4.8 plus 19.2, that gets me 24 volts. And you can see that the larger resistance dropped the most amount of voltage. Now we'll move on to this guy, resistors 4 and 5. Again, this is the larger resistor, so it should drop more voltage. And we simply say that the 3.2 amps is flowing through both of them. Current in that series circuit between 4 and 5 is the same. So we can figure out our Ohm's law, voltage is equal to I times R. So I'm going to go 6 multiplied by 3.2. I get 19.2 volts here. And that's coincidental. And then obviously this guy, 3.2 times 1.5, 4.8 volts. All right. So at this point we have all of the currents and all of the voltages necessary from this circuit, and it just took a little bit of creativity to get there. So trying to position this so we can see it all and pop all those numbers into the table. Okay, so the voltage that we would get across resistor number 1 is going to be 24 volts, and that's going to be 12 amps. The total current in this guy is going to be the 16.8. Voltage across resistor 2 is going to be 4.8 volts, and that's going to be a current of 1.6 amps. Across resistor 3, voltage is 19.2 volts and 1.6 amps. Voltage across resistor 4, 19.2 and 3.2 amps. Across 5, again it's 4.8 and 3.2 amps. Okay, so that was one of the dreaded series and parallel circuits, and the last thing we have to do is to go through and calculate all of the power for each of these. So that's simply taking the current times the voltage for each one. Alright, so I went through and just paused the video for a second there and did that routine business of calculating the powers for each of them. Again, voltage times current for each. And the interesting thing is here, regardless of what kind of circuit it is, if it's series, parallel, what have you, powers are always going to be additive. It's the case for both series and parallel circuits. So if we want to double check our work after going through one of these circuits and say, you know what, the total power is equal to the sum of all of these, it should be this 403. And that's a great way to check your work on any of these circuits. So that was one of those dreaded series parallel circuits. I know it takes a little bit of time to get used to it, but I think if you guys do your due diligence and you redraw the circuits as we had shown here, break them down, figure out what elements are in simple series or simple parallel, so that procedure is pretty interesting, where you figure out, okay, these are in series, so we can combine them using series formula. These were in series, we could combine those using series formula. These three values are all in parallel. We can combine them using parallel formulas. And your goal is to get down to one resistance value, your total resistance, using only series or parallel, one at a time. Redraw the circuit. And again, once you get used to it, you may not have to redraw the circuit every time, but when you're first starting out, it works great. Once you've gotten down to your total resistance, then work it backwards. Start popping in those currents and voltage values. Again, you're looking for one or the other, current or voltage. What can I find? In this case, we could find voltage because they're all in parallel. They'll all have 24 volts, so we calculated the amps. Plug those numbers in here. We found the amps through this branch, so we could say, oh, well, in a series circuit, the currents are the same, so we can then calculate voltage drop. So break it down to its simplest form, a resistance total, then work your way backwards, trying to find either voltage or current, until you've got everything solved. And really what we're doing here is making your brain think about series and parallel circuits and how do the voltages break down in there. So in the future, you'll be able to look at a schematic and you'll be able to say, oh, okay, I've got a bunch of loads in parallel. This one is a lower resistance, so I know it's going to be pulling more amps, and you kind of have an intuition about what's happening inside of the circuits. So good luck to you guys, and there's a bunch more worksheets like this that you can chew through that are in D2L. Check them out, and we'll catch you next time.